What's up, everyone? Welcome to AP Statistics. In this video, we're going to talk about the effects of transforming the values of a data set has on summary statistics. So I know this whole idea of this looking at analyzing quantitative data has been a long unit, long lesson, but one more last video here to talk about. So what we're talking about here is what happens when you transform your data. Now, what do I mean by transforming my data? Well, there's actually two ways to do that. One way is making the same change to all of the values in the data set. Maybe I add 5 to all the values. Maybe I subtract 6 from all the values. Maybe I multiply all the values by 3. Maybe I divide all the values by 4. Again, you're doing a mathematical operation, subtraction, division. You're doing it to all of the data values. Maybe it made a mistake. Maybe your scale was off and you're like, oh, I got to add 5 pounds to all the weights. Or who knows? Maybe it's a test and you want to give a bonus point. Or maybe it's a test and you want it to be worth double the points, so you multiply by 2. The second way you could transform the data is by, adding one new value to the data set or changing one value that may have been wrong. So maybe you realize, oh, I had 99 pieces of data. I was supposed to have 100. I forgot one. It got lost in the paperwork. So I'm going to add that new data into my values. I forgot about it. Or maybe you typed one of your data values in wrong. You typed it as 7. It was supposed to be 7D. So I got to go back and change it to a 7D. So, when you change one value, how does that impact your data? So again, what we want to do is we want to examine how these changes affect the summary statistics. Mean, median, mode, standard deviation, IQR, range, all that fun stuff that we've been learning about. All right, so let's start with addition and subtraction. This is actually very simple and very common sense. If we were to add or subtract a constant to all of our values in the data set, what would happen? Well, first off, why would we do this? I gave some examples a moment ago, but maybe a company wants to give everybody a $500 raise. So that means everybody's salary is going up $500. So here's what's important. Measures of center, mean and median, will go up or down by that exact same value. So if everybody gets a $500 bump in their raise, well, guess what? The mean is going to be $500 more. The median is going to be $500 more. Duh, that's pretty simple to understand. Q1 is going to be $500 more. Q3 is going to be $500 more. So even measures of position, if all of your values are going up 500, then your center and your measures of position, that first quartile, that third quartile, they're all going to go up $500 as well. However, this is important. Measures of variability, which are range, IQR, standard deviation, these are not going to be affected at all. These will stay exactly the same. And the idea is very simple. All we're doing is we're moving our data all up as a collective group. If all of your data is moving up or down as a collective group, you're not changing how that data is spread out at all. So I want to go and actually show you an actual example of this so you can believe me. So here is a set of test scores. In yellow, there is lots of values. You can scroll all the way down. I'm not going to show you them all. But I have the mean, 78.5, the median, 81, standard deviation, 14.587, range, IQR, min, Q1, Q3, max. I got it all listed there for you. And I even have a beautiful histogram of all this data. Definitely skewed to the left. Now, if I just leave everything the same, no changes, well, my new centers, my new spread, my new positions are all staying the same. Like if you don't change your data, everything stays the same. But watch this. I'm going to click on the next slide here, and I'm going to add 10 to all the values. Boom. Look what happened. I added 10 to every single one of my scores. So I left the original summary statistics on the left, but look at the new ones. The mean is now exactly 10 points higher. I gave everybody a 10-point raise. It makes sense the mean is exactly 10 points higher at 88.5. The median is exactly 10 points higher at 91. But notice spread, standard deviation, literally exactly the same. Range, IQR, exactly the same. But again, measures of position, like the min was 30, well, now the min's 40. The max was 100, now the max is 110. If you're adding 10 to all the values, measures of position, min, Q1, Q3, max, they're all going to move up 10 as well. And check out the histogram. It's still skewed left, but here was the original histogram. Here's the new histogram. Original, new. You literally are just sliding the entire histogram over 10 units because I added 10 to all the values. So again, not changing the spread at all. Pretty cool, pretty simple. Hopefully you guys like that demonstration there. Now let's talk about multiplication and division. Now, please remember that division is really multiplying by the reciprocal. So even division can be looked at as multiplication. All right. If we were to multiply all values in a data set by the same value, what would happen? All right, why would we do this? Maybe we're just converting, right? If you're going to convert from pounds to kilograms, you have to multiply by 2.2, or actually it's the opposite. If you're going from kilograms to pounds, you multiply by 2.2. Or you could go from pounds to kilograms by dividing by 2.2. Again, you're just multiplying by a conversion factor. Even if you're going from feet, you multiply by 12 to convert to inches. So sometimes we're just converting. Or like I said, maybe it's a test, you want to give a bonus point. Who knows? Now, what happens when you multiply? Measures of center, mean and median, will both multiply by that value. Like, duh, if every value is getting multiplied by 2, the mean and the median are going to get multiplied by 2 as well. Measures of position, percentiles, Q1, Q3, min, max, those are all going to get multiplied too because they're actual measures of spots. Like there's a spot in the data, but if all the data gets multiplied by 4, that spot's going to get multiplied by 4 too. But here's the next thing. Measures of variability, they get multiplied as well. So when you multiply, everybody gets affected by that multiplication. Because when you multiply, you are definitely affecting the spread. You're definitely getting more spread out. And to prove that to you, I have another example. So here's that original sheet of our data scores in their originality. Imagine if I wanted to make this test a double grade, like I wanted it to be worth more. So I'm going to double everybody's grade. Everybody's grade gets multiplied by 2. Check out the scores here. So once again, everybody's value in yellow got doubled. The mean was 78.5. The new mean is exactly double that, 157. Grab a calculator if you don't believe me. The median was 81. The new median is exactly double that. But now check out spread, standard deviation range, and IQR. All of those values also got doubled. So multiplying all of your values affects spread as well. And then position, of course, as well, all of the values. So basically everything gets affected by multiplication. Now, I actually had to scroll down here to show you the histogram because it's so much more spread out. Look at that, right? Here's the original histogram. Multiplied all by 2, it really spreads out. My new min is now 60 because it was 30 times 2. My new max is 200. That's a much bigger spread. Originally, it went from 30 to 100. That was the original spread, 30 to 100. But when you double it, oh, by the way, that's a difference of 70, right? But if you double it, now you're going from 60 to 200. That's now a 140 spread. So your spread definitely doubled. The histogram still skewed left. So that's another thing I should mention. Shape doesn't change at all. No matter what you do to your data, the shape is going to stay the same. But its spread, its center, all of that could definitely change. So, moral of the story, addition and subtraction affect measures of spread. Whoa, oh my gosh, can't believe I said that. They don't affect measures of spread. Addition and subtraction only affect measures of center and position, not variability or spread. Multiplication, however, affects everybody. Pretty simple. All right, now let's look at an example so we can really understand this. So this is an example where I'm not giving you all the data. I'm just giving you the summary statistics. Mean, standard deviation, median, Q1, Q3, all the fun stuff. Okay. Now, imagine we're going to convert this. And I'm actually going to convert this data combining. Check out what I'm going to do. This is crazy, right? I'm going to first, order of operations, I'm going to first take an old score and multiply it by 3.5. And then I'm going to add 8. So I'm actually combining the two things we just learned. So imagine these, I don't know, maybe these are test scores again. And imagine you're John. And John, you on this test, maybe it's not, let's look at this as points. These are points on a test, right? Not percentages, because if the average was a 33%, then that's a pretty crappy test. But maybe it was like a 40-point quiz and 30, I don't know, whatever. Who cares? But let's just say John's value was a 40. That was John's value. How would I get John's new value? Well, I'd take 3.5, times it by 40, add 8. John's new value would be 148. 3.5 times 40, add 8. John's new value is 148. So my question to you is, if I transform the data by combining multiplication and addition, how are my values going to affect? Well, here's the thing. The addition of the 8 will not affect standard deviation, IQR, or range. The multiplication will affect everybody. The adding of 8 will affect everybody except for standard deviation, IQR, and range. So the mean is going to be 33 times 3.5 plus 8, because the mean gets affected by multiplication and addition. So my new mean is 123.5. Standard deviation, 17. Standard deviation does get affected by multiplication. So I'm going to multiply by 3.5, but I'm not going to add the 8. The new standard deviation would be 59.5. Median, 28. Multiply by 3.5 and add 8, because the median is affected by both, 106. Q1 would get affected by both. Q3 would get affected by both. I'm just trying to save some time here. The IQR, once again, I'm going to take the IQR of 22. It would only be multiplied by the 3.5. You would not add. Addition does not affect spread. So the IQR would be 77. The min would be affected by both. The max would be affected by both. But once again, the range, 72, multiplied by 3.5. Do not add the 8. It would be just 252. So essentially, the only thing you got to really focus on is this. Like one thing I tell students is, I'm very nervous saying this, but multiplication, addition affect everybody. Big but addition does not affect standard deviation, IQR, and range. Those are the measures of spread. So for the most part, everybody does get affected, except those three things. Addition or subtraction does not impact them at all. All right, now let's talk about that second way that you can transform data. This is by adding a new value or maybe changing one of your values. Now, any new value added to the data set will affect the mean, because the mean takes everybody into account. But if that value is an outlier, it's going to affect it more. I think of the mean as like a balancing act, right? The mean is here's the mean, it's trying to keep a nice balance. So if you add a value way out here, that's really going to tip the scales, and the mean is going to have to move higher to continue to balance it. But if you add a value close to the mean, it doesn't have to make as much as an adjustment to take care of it. It's still going to adjust a little bit, but not nearly as much. And the same thing is true for standard deviation. The standard deviation will get affected as well, because the standard deviation takes every single value into account. So if we add a value that's way far away from the mean, then the standard deviation, which measures how far data is from the mean, is going to have to get bigger, because you're adding a value that is way far from the mean. But if you add a value that is close to the mean, well, that's not going to have as much of an effect. The standard deviation might actually even go down a little bit, not a lot, but a little bit, because again, you're adding a value close to the mean, and the standard deviation measures how far data is from the mean. Now, the median and the IQR actually will not change that much with the addition of one new value. Because remember, the median just cares about being in the middle. The median just says, I want 50% on the bottom, I want 50% on the top, and I want to be right smack dab in the middle. I don't even care what the numbers are, I just want to be 50-50. So if you add a new value all the way over here, then honestly, the median might get affected just a smidgen, but at the same time, it doesn't really care if that number's an outlier or not. It just says, hey, I need 50% on both sides. So if you add one number to the right, I might have to shift a teeny bit to stay in the middle, but not really that much. And the same thing with the IQR. The IQR focuses on the middle 50% of your data. So adding a value to the outside isn't really going to affect it. Now, if you add a value to the inside, it might change a little bit, but again, not that much. I mean, by definition, the median and the IQR actually do not take every value into account, right? They just want to be in the middle. Whereas the mean and standard deviation, they literally, the definition, the formulas take all of the values into account, okay? So it actually really matters. All right, I actually have a cool example to make sure you guys understand this as well. So this is going back to that original one, right? My original test scores, nothing has changed, right? The original and the new, exactly the same. Check this out though. I'm gonna add a test score. Now, if I add an outlier, remember the max was 100. So maybe we add a new score of 115, somebody who just did off the charts. So check this out, this is super cool. As soon as I hit enter, look at the histogram, we see a new new data point got added all the way to the far right. Now look at the mean. It was 78.5. It went up to 79.16. Again, that's a significant, I mean, not a huge change, I get, but it's definitely adjusting for that value. And let's just do something crazy, right? Let's add 500 as the new value. Look at that. Now the mean had to really adjust. That mean went from 78.5 to 86. That's a huge change because of such an outlier. Let me delete that and go again. Now watch what happens to the median. If I add an outlier like 115, yeah, the median went up from 81 to 82, but that's just because I added a value on the right. So the median's gonna have to move over a little bit to keep that 50-50. But check this out. If I add 1,000, notice the median still stays at 82 because the median doesn't care how far away that value is. It just cares that, all right, I added a value to the right, so I'm gonna have to move over a smidgen to adjust. But look at the mean. It went from 78.5 all the way to 95 because of that huge outlier. Check out the standard deviation as well. By adding such an enormous outlier, the standard deviation went from 14.5 all the way to 125 because the standard deviation is how far typical data is from the mean. And when you add a value that is way far from the mean, the standard deviation has to get bigger to try to accommodate for it. Notice that the min and the Q1 did not change because I added a value on the right side. So since I added a value on the right side, the max obviously went up to that outlier. But now let's do this. Let's add a value that's just kind of like all the other values, right? What's typical? About an 85 is a pretty typical test score. So if I add an 85, not much changes. Not much changes at all. The mean changed a smidgen because the mean has to take everybody into account. But again, the median, really small change. Standard deviation, it changed a little bit. Now notice, the standard deviation actually went down a tad. Why did it go down? Because I added a value that was close to the mean, right? So now the standard deviation, adding a value closer to the mean, standard deviation goes down a little bit because standard deviation measures how far data is from the mean. And then again, look at my Q1 and Q3. They didn't change at all because I added a data right in the middle. So the middle 50% of the data doesn't really get changed. So I thought that was a cool example to show you guys as well. All right, I want to end with one more type of problem here. This is kind of a nice summary of everything we've done. I really want to make sure you guys understand how to work with summary statistics. So, here is that summary statistics. Now, I don't know my data. I don't even know my sample size. I just know that this is what the summary statistics are. So one question I could still ask you is if there's any outliers. So once again, you would take that lower fence of 20, or the lower Q1, minus 1.5 times the IQR of 22. And this is going to find that lower fence. 20 minus 1.5 times 22, I'm doing it on my calculator right now, is negative 13. And you'd say, well, if the min is 15, well, there's obviously nothing lower than 15, so nothing could possibly be lower than negative 13. So that means there's no lower outliers. Now, what about upper outliers? I'm going to take Q3, 42. I'm going to add 1.5 times the IQR of 22, and I get 42 plus 1.5 times 22, and I get 75. Now, are there any values bigger than 75? Well, the max is 87, so absolutely. But listen to what I'm about to say. The max is definitely an outlier. Could there be more outliers? Maybe. I don't know the data, right? Q3 stops at 42. So I'm thinking about a box plot, right? Here's my box. Here's Q3 stopping at 42. The max goes to 87. 87 is definitely an outlier, but I don't know the other values in between Q3 and that max. Maybe there's an 86, maybe there's an 80, maybe there's a 76. 76 would be an outlier because it's above the upper fence. So I just don't know, but that's the drawback of not knowing all your data. But I do know for sure there's at least one outlier at 87. Now, what would you say about the shape? Well, remember, let's talk about this. I want you guys to understand that you don't need a graph to understand shape. First off, notice the mean is bigger than the median. That immediately tells me that something is pulling that mean to the larger numbers. That automatically tells me I might be a little bit skewed to the right. And I've also established there's an outlier to the right that's going to yank the mean up a little bit, causing skewness. But here's this. Check this out right here as well. Now notice that the median is 28. Q1 is 20. So the median is only 8 values above Q1. But check out Q3. Q3 is much bigger. It's 42, which means it's 14 values away from the median. So again, I'm thinking about that box, right? And here's Q1 at 20. Here's the median at 28. And Q3 is bigger. That's an 8 difference right here. It's a difference of 8. Well, from 20 to 42, I might be being a little bit of exaggerating here, but that's a difference of 14. That means the right side of that box is going to be more spread out. That's another sign of skewness. So I'm definitely skewed to the right here. And again, I didn't need a graph to see that. I could just knew it from two things, looking at the mean being higher than the median and looking at the boxes, Q3, Q1, and the relationship to the median. Q3 is definitely further away from the median. That's what tells me I'm definitely skewed a little bit to the right. Okay? So pretty cool that we can learn all that from summary statistics. All right, that's the last video for this. See you guys later.